In this video, we're going to look at something called a rate law. A rate law is an expression. It's going to be used to show how the reaction rate is dependent on the concentration of the reactants. What if I double the concentration of a reactant? How does that affect the rate? What if I triple the concentration of a reactant? How does that affect the reaction rate? Now, typically, a rate law expression is going to kind of look like this. This is technically the rate law. From this arbitrary reaction, A plus B produces some kind of product. Now, typically, these rate law expressions only include the reactants. Now, again, we could put products in, but we kind of looked at in the last video how everything should be proportional according to the balanced equation. The other reason why we want to study primarily the concentration of the reactants kind of refers to something that we're going to look at in the next chapter. As some reactions progress, obviously you form products. As the concentration of the products increases, sometimes there's the chance that those product particles can collide and reform the reactants. So in a sense, it kind of sends the reaction backwards, where some of the products go back to the reactants. We don't want to study any of that. So we often study these reactions soon after they're started, so that the reverse reaction really isn't significant. That hopefully we're just going forward, turning reactants into products. So we're really only going to study the concentration changes on the reactant side. So again, here's kind of an example of what this rate law looks like. It's a bunch of symbols. Here's what they stand for. When you see something in brackets, now it's usually going to be like an element or a compound. We mentioned in the last video that brackets represents concentration. Concentration is measured in molarity, which could be the big capital M, or maybe just that moles per liter. Other things that you'll note in this expression, there's these little exponents by A and B. They're called reaction orders. We're going to look at determining these guys in a minute. These reaction orders will show us how changing the concentration of that particular reactant affects the reaction rate. So what if I double the concentration of A? What does that do to the rate? We'll talk more about those guys in a minute. K is called the rate constant. The rate constant should be constant. We'll look at that guy in a few minutes. And then finally, this is important. The value of the constant and those reaction orders, those little exponents, N and M, those must be determined from experimental data. The constant and the reaction orders, those little exponents, those have nothing to do with the ratio from the balanced equation. Now, when we looked at general rates in the last video, they did. The rates were proportional to the balanced equation. But that may not be the case as we start changing the concentration of one particular reactant. So now we have to look at experimental data to figure out how changing the concentration of a reactant affects the reaction rate. So let's look at some data, shall we? Okay, so here's this fake reaction with A and B. They form some products. We don't really care what they are. But you'll have data that looks like this. Somebody ran 3 trials. We changed the concentration of A and B and studied the reaction rate. And obviously the constant is constant, which we'll talk about the constant later. So here's what you do. That initial expression, that initial rate expression kind of looked like this. The rate law, R equals K the constant times concentration of A raised to some power times concentration of B raised to some power. N and M are called reaction orders. And again, they reflect how changing the concentration of that particular reactant affects the rate. So we sub in to that equation using trials of data where the concentration of A changes, but B stays the same. Let's say I want to find N. Suppose we should specify that. Let's say we want to determine N. Okay, so we're looking at changing the concentration of A. So again, we have to find two trials where A changes, but B is a non-factor. So we want the concentration of B to remain constant. So B remains constant in trials 1 and 2. A changes, the rate changes. And obviously the constant is constant. So notice like here, when we sub in, they didn't numerically sub in for the constant because it's constant. Because it's not going to change, and it's going to cancel out in a second. Otherwise, does this make sense? Watch where we get these numbers from. So let's say I sub this data into the rate law. R is the rate. So for trial 1, it's the 1.08 times 10 to the negative 5th. K is the constant. They could have put the numerical value in. I just didn't. I've got the concentration of A raised to some experimental power, which we will determine in a minute. And this is the concentration of B in trial 1. Then we do the same thing with trial 2. We've got the rate for trial 2. K is the constant. This is the concentration of A raised to a certain power, and B raised to a particular power. Okay, so now watch what happens if we compare these. Here's where it gets good. Let's compare these two, trials 2 and 1. So it looks like between trials 1 and 2, the reaction rate doubled. So we're simplifying this. K is constant, so it's going to cancel. That's why they didn't sub in the numerical value of K. If it's constant, it's going to cancel anyways. It looks like concentration of A doubled, while B stayed the same. So if B stayed the same, we should also be able to cancel it. So now look what happens when this is simplified. 2 equals 2 to the nth power. From that experimental data, we can determine the value of N. And again, this is very high-level math. N must be 1. So we say then that this reaction is first order with respect to A, reactant A. Those little exponents are called reaction orders. Here's what it means. In a nutshell, it means this. If you double the concentration of reactant A, you double the rate. Experimentally, that's why N is 1. This would be the same. Make note, another example. What if you triple the concentration? If you triple the concentration and you triple the rate, that would be first order. You would sub in experimental data, kind of like what we did above, and as you simplify things, it would look like 3 equals 3 to the first. It must be first order. The exponent is 1. You could quadruple the concentration, and if the rate quadruples, it's first order. That exponent is 1. Now, to be honest with you, when I have to determine the order of a reactant, I don't sub in like what we did on top. I don't sub into the rate law expression and cancel like terms. I just do it by inspection. Although, I'm kind of following the same rules. I look at my lab data. If I want to study how changing the concentration of reactant A affects the rate, I find 2 trials. I want B to remain constant. I want A to change. So I doubled the concentration of A. Look at what happens to the reaction rate. If you double A and you double the rate, We call that first order. So again, you can totally do this by inspection. You don't have to numerically sub in to that original rate law expression. That's what first order means. You triple the concentration, you triple the rate. You double the concentration, you double the rate. That exponent would end up being a 1. All right, so now let's move on and study B. So down below, we've got some data again. Let's study the order of reactant B. So we would find 2 trials of data. This time we want A to remain constant, and we want B to change. So I look at my experimental data. A needs to remain constant. B changes. And I want to study how that affects the reaction rate. So you could sub in to that original rate expression, which somehow kind of looked like this. R equals K, and then we had A to the nth power and B to the m power. So again, that n and m, those orders have to come from experimental data. Okay, so if you wanted, you could sub in. You pick the data from those 2 trials. You've got the 2 rates. K is constant, so obviously that could cancel. A remained constant because we're studying B. So now let's scale it down. Let's simplify things. The rate quadrupled when we doubled the concentration of B. So we doubled the concentration of B. 0.1 to 0.2, the rate went up 4 times. So again, now looking at the data, what is this value of M? M's got to be a 2. It's to the second power, right? 2 to the what power equals 4? 2 to the second. Again, I mean, conceptually, it's something that you've never done before, but mathematically, not so bad. Here's what it means when we say that something is second order. So we would describe this as B, reactant B, is second order. Or the reaction is second order with respect to reactant B. It means this, that if you double the concentration, the rate goes up by a power of 2. The rate will go up by 4. It quadruples. Now again, this could be all kinds of different combinations. You could have something like, I don't know, what if you did this? What if you triple the concentration? If you triple the concentration, and the rate goes up by 3 to the second power, the rate goes up by 9. The rate increases by 9. That's 3 to the second power. That's second order. Or another one. What if we increase the concentration by 4? We quadruple the concentration. What if the rate increases by 16? That's 4 to the second power. Now, most commonly, we double the concentration and we quadruple the rate. But it could be anything where that power ends up being a 2. Now we triple the concentration and the rate goes up by 9. 3 to the what power? Oh yeah, 3 to the second power is 9. And again, you could do this by looking at experimental data. You don't have to get this by subbing in like they did above. I just look at the data. Look at the data conceptually. I want A to stay the same and I want B to change. So that kind of helps me pick which trials of data I'm going to study. I'm going to study trials 1 and 3. A is not a factor. B doubles. The rate goes up by 4. Second order. That exponent must be a 2. Okay, so if we put all this together, my overall rate law looks like this. Rate equals, K is a constant, A to the first, B to the second. We say A is first order, B is second order. If you double the concentration of A, you double the rate. If you double the concentration of B, you quadruple the rate. Now, other things that you might see, this is, I don't know, kind of useless, but it does come up every now and then. Sometimes they'll ask you, what is the overall order of the reaction? To get the overall order, you just add up the individual orders. And again, you could have one reactant, you could have 3, 4, 5 reactants. The overall order of the whole reaction is just the sum of those little orders. By far, these are the most common rate orders, and they're the only ones that you will ever need to deal with. There are others, and you can have half orders and kind of crazy things like that, but these are the only ones that you need to be familiar with for the AP test. First order, if you double the concentration, you double the rate. Second order, you double the concentration, you quadruple the rate. And there is something called zero order. Zero order would mean you change the concentration and the rate stays the same. The rate is not affected by changing the concentration of that particular reactant. We'll talk more about zero order reactants in a little bit. So other things that we might be asked to do then. Using this rate law that we determined experimentally, those 1 and 2, those orders have to come from lab data. Confirm the value of the constant. What are the units of the constant? Excellent. So here was my rate law. R equals K. A to the first, B to the second. Okay, so now you should be able to pick any trial of data. Sub in from any trial of data. Obviously, the constant should stay constant, so it doesn't matter what trial you pick. You just sub in, and we're going to leave K as our variable. So, I don't know, let's pick this one. Rate. You could say a molarity per second, moles per liter second. K is going to be my variable. Concentration of A. I just randomly picked trial 1, where A is 0.1 molar, B is 0.1 molar. Here's my rate, and we're going to experimentally try to determine this constant. All right, so I got 0.1. That's going to the first. 0.1 for B. That's going to the second. I'll put that in there. This was B, this was A. All right, so let's plug it in our calculator and solve for K. So we've got 0.1 to the first, 0.1 to the second. K equals 0.0108, which is the same as what they had listed before. They had listed 1.08 times 10 to the negative second. That's exactly what we got. And again, this should be true of any trial of data. You can plug in any trial. So now here's the stinky part. The part that annoys me. The units of the constant. I find this totally useless, but they always ask for it on the AP test, so you might as well get used to it. The units of the constant depend on the orders of the reactants. So here's what you got to do. Sub in to that expression with just the units, and then we're going to algebraically solve this for K. Okay, so initially my rate was like units of meters per second. I'm going to solve for the units of the constant. And then I'm going to have M. I'm going to say like molarity of A to the first. And I'm just going to say M molarity of B to the second. So this, we kind of simplified it. M to the third. So now you just got to do the algebra. It's annoying. And again, I find these units completely useless. But it is something that they ask for on the AP test all the time. So you might as well get used to it. So we're going to have something that looks kind of like this. We're going to have molarity per second. I'll grab myself a little more room here. And then we're going to divide that by molarity to the third. And that should be the value of K, or the units on K. So you could simplify this and you could say like molarity per second times 1 over molarity to the third equals K. And then I could simplify that. So I could get rid of this guy. I could bring this down to a 2. And there's lots of different ways that you could write this then. Options. You could say K equals 1 over, you could say like seconds times molarity to the second power. You could do that. You could write that as seconds to the negative first times molarity to the negative second. You could do that. You could have subbed in moles per liter for molarity. That would have been fine. But the units of the constant, I think that's the best way to do it. Take your expression and now just algebraically sub in the units for all the variables, molarity to the first or the second or whatever it might have been, and just solve it then for K, the constant. So here is my numerical value. And either of those would be acceptable units for the constant. Or again, you could have plugged in moles per liter for the big capital M molarity. I think this just makes it a little bit more concise.